All right, so to pick up where we left off, what we're trying to do is determine what the square S turns into once we map it into the xy plane using our transformation defined by these functions here. Now, there's a couple of ways to go about this, but the way that I'm going to approach it, which is going to make this I think the most straightforward we can make it, is to take these two functions and actually solve them for v and u. So in other words, I want to try and represent u as a function of x and y, v as a function of x and y. Now notice v is pretty much done already. V is equal to x. But I need to figure out a way of solving for u. So notice here, if I were to divide both sides of this by 1 plus v squared, I get u equals y over 1 plus v squared. Whoops, there we go. Then I use the fact that x is equal to v to make a substitution. I can substitute an x in for that v right there. So u is equal to y over 1 plus x squared. Similarly, v is equal to x. Okay? And so now what I'm going to do is basically just make some substitutions to get each edge of the boundary in the xy plane corresponding to the or that are the images of the boundary edges of this square S. So let's start with this one on the bottom here. Down at the bottom, v is equal to 0 and u is between 0 and 1. So I'll write this like this: v equals 0, u is between 0 and 1. Okay, so in this first case, if I go over here, if I were to plug 0 in for v, that would imply that x is equal to 0. And if u is between 0 and 1, then I can substitute this expression, y over 1 plus x squared, in for the u there. Y over 1 plus x squared is between 0 and 1. Now use the fact that x is equal to 0 to show that this is just y over 1 or y. Okay? So this part of our boundary maps to a boundary in the xy plane where x is equal to 0. Think of the line x equals 0. That's the y-axis, where y goes from 0 to 1. So as y goes from 0 to 1, we're talking about this part of the y-axis. So this boundary, or this edge of the boundary of S, gets mapped to this edge of the boundary of this new region, which I haven't given a name to. But let's do that again with another edge. Let's maybe take a look at this this edge right here, where v equals 0, or I'm sorry, where u equals 0 and v is between 0 and 1. Okay, so if u is equal to 0 and v is between 0 and 1. So same idea. U, remember, is this expression right here. So let's actually work with the v first. If x is equal to v and v is between 0 and 1, then I can say x is between 0 and 1. Okay, now what can we say about y? Well, again, if I were to substitute u equals 0 in here, I would get 0 equals y over 1 plus x squared. Multiplying both sides by 1 plus x squared shows that y is equal to 0. Okay, so together these two sets for x and y kind of give me a description of what I want my boundary to look like. Y equals 0 is the horizontal line passing through 0 on the y-axis. That is the x-axis. And if we restrict x to be between 0 and 1, then we're talking about this piece of the x-axis right here. Okay, so this boundary of S becomes this boundary of our new region. Okay, we have two more edges to consider. Let's look up here. V equals 1. And U is between 0 and 1. Okay, so again, if U is between, well, let's start here. If V is equal to 1, X and V are equal to each other. So this would say that X is equal to 1. And then again, up here, when U was between 0 and 1, we got this. We substituted Y over 1 plus X in for U. So we got 0 is less than or equal to. Now, if X is equal to 1, I can plug that in for the X right here. And I get 1 plus 1, so I get Y over 2. Which tells me that Y is between 0 and 2. Okay, so these two determine the next part of my boundary. So if X is equal to 1, then we're talking about the line segment, the vertical line passing through 1 on the x-axis up here. And if we're restricting Y to lie between 0 and 2, then let me put 2 up here. And that line segment goes only this high. Okay? Finally, we have to deal with this last edge right here, where U is equal to 1 and V is between 0 and 1. So if U equals 1, V is between 0 and 1. So again, if U is equal to 1, or actually, let's start with the V. This means X is going to be between 0 and 1 because X is equal to V. And then if I go to this inequality right here, substitute, the wrong one. If I set U equal to 1, that's this. Y over 1 plus X squared equals 1. Solve that for Y. Y is equal to 1 plus X squared. So together, these two conditions describe the curve that I want to use for my boundary. The curve is a parabola, y equals 1 plus x squared. It looks like y equals x squared, but shifted up 1 unit, so my vertex is here. And then we only let x go from 0 to 1. Well, if x is equal to 1, if we plug 1 into this, we get 2. So the point 1, 2 would be on that parabola, and we end up with something that looks like this. Okay, so just point out where all these sides are. This is the side x equals 1. This looks like x equals 0 here. This looks like y equals 0. And this looks like y equals 1 plus x squared. So when it says find the image of S under that transformation, let's call that region R. It doesn't say in the problem to call it that. But the boundaries of S will map to these boundaries here. And then, again, a property of C1 transformations is that all of the points interior to S will will have images interior to R, and every point in R interior to R will be the image of something in here. So this entire square is going to map to this entire region right here. Okay, I could try and describe that region as a set. I could describe it as a type 1 or a type 2 region, but I'm going to just let the graph be my answer, the graph of this region. All right, now let's try another example. Kind of go in the other direction this time. So here, I'm going to let R be the parallelogram in the xy plane with the following vertices listed here. What I want to do is find equations for a transformation T that maps a rectangular region S in the UV plane whose sides are parallel to the U and V axes onto R. So I believe there's 1 or 2 homework problems kind of like this, and being able to do this is going to help us with a problem that comes up later. But the idea is that we're starting with a description of a region in the XY plane. So the region that we're starting with is the image. We don't yet have the region in the UV plane that this image comes from. So I'm going to start by plotting some of these points. Let's say 0, 0 is here, Let's go 1, 2, 3, 4, like that. 1, 2, 3, and then 1, 2. So I have a point at 4, 3, that would be here. I have a point at 2, 4. I need the fourth point up there, so that's going to be like here. I should have a point at -2, 1, so that's going to be here. Okay, and if I connect these points, I should get that parallelogram that we're calling R. Okay? Now, each edge of this parallelogram, I can find an equation for it. And again, we're in the xy plane right now. So what I would need to do is use the point-slope form of a line to find the equation of all 4 of these lines using these vertices that were given here. If I were to do that, and if I were to put the equations for each one of those in standard form, I would get the following. I get x plus 2y equals 10 for this line here. I would get 3x minus 4y equals -10 for this line. 3x minus 4y equals 0 for this line, and then for this line here, I'm going to get x plus 2y equals 0. Now, it might seem a little unusual that we're using standard form for these lines, but there's a reason for that, and it's going to show up in a minute. What I want to do is find in the UV plane. So this is my UV plane. A rectangle somewhere in here, and notice it doesn't specify where it's supposed to be. It just needs to be a rectangle, but the edges of that rectangle need to be horizontal and vertical. That's the part where it says they need to be parallel to the U and V axes. Not only do I need to find a rectangle in the UV plane, I also need to find a transformation T that will take that rectangle and map it to this parallelogram R. Okay, so the way that I'm going to do that, I'm going to take a look at the equations that I have here. You notice 3x minus 4y shows up in a couple of them. That's because these two lines are parallel, but the constant terms are different. So if I were to imagine the points interior to R, I could think of all those points as lying on lines that are parallel to these two. And any line parallel to those two is going to have an equation that looks like 3x minus 4y is equal to some constant between -10 and 0. If I had 3x minus 4y equals -9, that would give me some line right around here. So what this says is that for any point in R, 3x minus 4y is between -10 and 0. Okay, similarly, if I look at these two parallel lines, x plus 2y equals 0, x plus 2y equals 10. If I were to think of R as being filled up by lines that are parallel to these two, then the equation of any one of those would look like x plus 2y equals some constant between 0 and 10. So similarly, I could say this. X plus 2y is less than or equal to 10, greater than or equal to 0. What this does is it suggests a change of variables. If I were to let, let's see, which one did I call u? If I were to let u equal 3x minus 4y and v equal x plus 2y, then I can make a substitution for u and v right here. Okay, so I could say that u is between -10 and 0, and v is between 0 and 10. First of all, notice that that creates a rectangle in the UV plane. So if I come up to the UV plane up here, if u is between -10 and 0, that's like this line segment right here. V is between 0 and 10. That's this. And that creates this rectangle in the UV plane. Okay, I'm just going to call that rectangle S. All right, so that's part of the problem, is finding a rectangle. And now these functions are where I'm going to get my transformation from, because these functions put a relationship between the points here that are given in terms of u and v and the points here that are given in terms of x and y. The only issue is that these are not represented correctly. I need x as a function of u and v and y as a function of u and v. So I'm going to look at this like a system of equations and attempt to solve that system of equations for both x and y. So notice, let's start by doing this. Let's say u, we know, is equal to 3x minus 4y. I'm going to attempt to solve for x, and in order to do that, I want to eliminate the y. So I have 2y here. If I were to multiply this equation by 2, I get 2v equals 2x plus 4y. Adding these together, on the left-hand side, I get u plus 2v. On the right-hand side, these y's cancel, and I'm left with 5x, which tells me that x is equal to u plus 2v over 5. Okay, if I do a similar system of equations, but then instead attempt to solve for y, not x, I go up here and I see that u is equal to 3x minus 4y. If I were to multiply this by -3, this equation here, then I would have u equals 3x minus 4y, and -3v equals -3x minus 6y. Up here. Adding those, I get u minus 3v equals -10y. Dividing both sides by -10, dividing by a negative, we'll just flip these around, so I can write this way. Y equals 3v minus u over 10. These two functions, where x and y are given as functions of u and v, describe the transformation. And again, remember, where it says find a transformation t, we're not going to come up with, t of uv equals, some big function. We just describe t using these two functions here. So this is the transformation, and under that transformation, this rectangle would map to this parallelogram R.